Um, Once again, the most critically important thing for you to be doing, all of you, or most of you, maybe not all, is to be taking proofs that I give you, studying them and rewriting them and producing the proof as if you were the author of the proof that I wrote. Very often, much too often, I'm getting stuff sent to me that I've done with you. And I've written letters back and I'm saying, but you know, you're messing up on this, but we did this in the classroom. Why are you writing this stuff? Why have you not studied and rewritten the proof I gave you? Stand on the shoulders of what I wrote for you and then move forward. And it will help you not only with finding a solution to a problem, it'll also help you with the writing. And I've got many people who are still having trouble with that. And you know, if you ever write, suppose that X belongs to S, you've got to ask yourself, why did I say that? If you decided I need to explain why every member of a given set is less than or equal to 50, then you would write, suppose that X belongs to S. You need to have that thought in your mind, I've reached a point at which I want to prove that something happens for every member of a set. And otherwise, don't write suppose. You write suppose when you are proving it for every statement. Be guided by the proofs that you are rewriting. Be willing to rewrite several times. I know that I still have to do it, and I'm slightly older than you are, like about 137 years older. But anyway, the fact is that you need to think about this kind of thing. If you need a member of the set in order to do something with it, and you know the set is non-empty, then you choose. If you're ever told that something exists, that's when you say choose. Suppose, for example, that a certain number X is not an upper bound of a given set E. And X is known for some reason. It's not an upper bound of E. What can you do with that information? X is not an upper bound. What does that tell you? It tells you that there exist members of E that are bigger. So how will you use that existence? You will write? Choose. Okay? If you want to talk about the supremum of a set, and you know this for some reason, that the set has a supremum. Supremum, that's a certain object. It means a particular thing. It means the least upper bound. That's not choose. You understand? That you're referring to something specific. If you want to say, listen, the supremum of the set, I want to call it Rumpelstiltskin. I want to give it a name. You're making a definition. You're giving a name to something. That's a we define. You want to call it W. We define W to be the supremum of a certain set because it's easier for you to type a W than to write SUP big A. See? That would be the reason. It's a definition. And you will get this kind of thing straight, and it's not just a matter of tormenting you with words, because believe it or not, this is what solves the math problems. And you think it's to do with 4381. I want to tell you something. When you are doing trig identities in pre-calc, or the law of cosines, or all sorts of things, you are actually using the same principles of writing mathematics. The only trouble is, was it taught correctly? I shudder to think how much answer in box, multiple choice, click the correct thing and send it with a computer to see whether you're right or wrong, all this kind of abomination that passes for mathematics teaching. Enough, I'll get myself into trouble if I speak the truth. Anyway, so we're coming back to where I was last time. I want to do the final case that there were a bunch of cases. Let me remind you, a set is called an interval if it's an interval. The following sets are intervals: the empty set, the entire number line. Any set that looks like this, the set of all numbers less than a given number C, or perhaps less than or equal to a given number C, or perhaps greater than or equal to a given number C, or perhaps greater than a given number C. Or there you have a couple of numbers A and B, A less than B probably, less than or equal to B, and we're looking at the numbers that lie strictly between A and B, or non-strictly, that you allow the B and you don't allow the A, or you allow the A and you don't allow the B, or you allow both of them. See, they are all of situations. These are all the different kinds of sets that we call intervals. And no matter which of these you take, it is clear that if you ever take two numbers that belong to an interval, then any number between them obviously belongs. That's a trivial fact of inequalities. If two numbers are both less than a given number C, then any number between them will also be less than C. This is just a matter of inequalities. But what we are setting about here, and what I did, some of the cases to explain last time, is that if you happen to know, suppose that you have a given set and you're given that whenever you have two members and a number between them, that the number between is forced also to be a member. In other words, that it is never possible to have a non-member sitting between two members. Under those conditions, the set must be an interval. And last time, towards the end of the day, when you were all exhausted, I proved this for several situations. When the set S is unbounded below and above, I showed you that S had to be the whole number line. That's an interval. When the set S is empty, there's nothing to prove. That's an interval. When the set S is unbounded below and bounded above, well, it's non-empty. Bounded above, it's got a supremum. If you call the supremum C, then you can explain that the set S is the set of all numbers strictly less than C, or perhaps it's not. Perhaps it's the set of numbers that are less than or equal to C. Those were the two cases. And maybe the set is unbounded above and bounded below. I did one of them and not the other. And then there is the case in which the set is bounded both above and below, and I promised I would do that today, and that's where I'm starting. Where is it? So I said done and done. One of these is a lie. One of these I left for you. You see, I did one in detail, and then I left the other for you. So what should you do? You should rewrite the one I did very carefully until that one is in your pockets. I'll tell you when you know it. It's when you didn't put anything down on the paper because you thought it was what Jonathan Lewin wanted you to put there. If you ever put something down on the paper because you're thinking that that's what I told you got to do, you're lost. You'll know when you write something, it's because you wanted to put it there. And you're confident that any claim you made that you could back up, you could explain. If you were a teacher standing before people and you were challenged, but I don't understand this, you could answer. And you rewrite my proofs until you can do, like for example, whichever of these, I did one of them. You rewrite until you can do it closed book, knowing why you are saying what you are saying. And it's possible that in the course of trying to do that, you might discover that maybe you can't get this together. And sometimes people send me something and they say, in class you did this, and here are the things you wrote, but at this position I don't know why this is permitted. that was permitted, but this, I don't see why this is permitted. Or how come you couldn't do this? Why couldn't you have just done something? Why did you not do, you ask questions. And then I can answer you. And I've been, most of the time, fairly good about giving prompt replies, and some of you know, very detailed replies. I sometimes sit forever writing all kinds of stuff for you. It's a lot of hard work, and I do it. And I do it usually quite quickly. I apologize for yesterday. I had no computer all day. I was sitting there climbing the walls, wishing I could reply to people. But I want you to know that that what frustrates me is if I write something to you and you've sent me 3 problems and all 3 have the same need and I write it for the one, I'd rather have one thing from you and then you get my reply and you work on it and you fix that problem and then you send me the other one standing on top of what I gave you. The comments for the one are then used for the other. If I send you something, I hope that you've read it and worked through it. So anyway, this is where we stand. I am assuming that S is bounded below and bounded above. And of course, am I recording? I jolly well am. Computer, it'll come back. I was hoping that the service we did on this machine yesterday would have overcome that problem. It has not. Thank you very much. So anyway, I'm assuming that S is bounded below and bounded above. And of course, I told you never write of course. It's too arrogant. Did I tell you that? Of course, we are assuming that S is non-empty. There's no point in fussing about the empty set because the empty set is an interval, you see? We want to prove that S is an interval. What kind of interval is it going to be? Bounded below and bounded above. It's not going to be an interval that goes from minus infinity to somewhere, or from somewhere to infinity, okay? Well, actually, don't you think it'd be reasonable that it should go from the inf to the soup? So this is what I'm going to do. I'm going to introduce some new symbols. We define A equals soup S. No, inf S. And B equals soup S. At least we get it in alphabetical order that way. I've defined A to be inf S and B to be soup S. I want to comment, we have long seen that when a set is non-empty, a lower bound of the set can never be bigger than an upper bound of the set. Reasonable? Why? Why? Let me remind you. Choose a member of the set. If you're looking at a lower bound, it's less than or equal to that member you chose. If you're looking at an upper bound, it's greater than or equal to the member that you chose. Okay? So certainly this number A notes that A is less than or equal to B. Just because I wrote note that doesn't mean that you should. When you rewrite this, you might write some explanation. You might say, look here, A is a lower bound of S and B is an upper bound of S. I'm going to tell you why I really know that A is less than or equal to B. Don't just slavishly copy my words that I say, note that, and you'll say, note that. The next step, note that. That's not the way you do mathematics. So anyway, suppose that S is bounded below and bounded above and non-empty. We are defining A to be inf S and B to be soup S. Now I'd like to make a comment. Whenever, I think it might be a good idea to draw a picture, and I strongly recommend lots and lots of pictures. Pictures to motivate what to do. You never really use a picture in any type of mathematics, even geometry. You never use a picture to make a conclusion. But you use a picture to motivate what you're going to write clearly, you see, in the logic. So here's a picture. That's what A looks like. And here's a bit of number line, and here's what B looks like. Okay? Of course, A could be equal to B, but I thought it might look cuter if I make A less than B in my picture. Okay? Now I'm going to say whenever X is less than A, whenever means for every. Do you understand? Whenever is a for every statement. Whenever X is less than A, we know that X cannot belong to S. Why? Because when I write this, you will write it and you will write some explanation. Because X is less than a known lower bound. The number A is a lower bound of the set. Actually, it's a very special lower bound. Inf S is the greatest lower bound. But who cares about that? Because A is a lower bound of S, numbers less than A are not allowed to belong to S. That's what lower bound means. Okay? So when you rewrite this, don't just say we know. Because Jonathan Lewin wrote we know, so you put we knows. Next thing, is this right? Sometimes people ask me, is this right? I say, well, did you understand it? I mean, understanding a proof is kind of like understanding a joke. You know? I say, did you laugh? So anyway. When X is less than A, we know that X can't belong to S. And there's a because, and you'll write more than I wrote. Okay? Now I'm going to tell you, whenever X is greater than B, that's in the no man's land up here. You see?
Should we still use the same variable?
There is no X anymore because like after the period, the X disappeared.
Okay.
That's why for every, you see? Whenever X is greater than B, we know that X cannot belong to S because B is a known upper bound of S. If you're bigger than an upper bound, you're not allowed to belong to the set, right? Sort of. So now I'm going to tell you, we shall now show, I'm going to announce, it is now my intention to prove. It is now my intention to prove that every number X satisfying the inequality A less than X less than B must belong to S. I'm announcing to you that this is what I now want to do. Okay? I'm announcing to you that I want to prove for every statement. I'm announcing to you that I want to prove that every number doing a certain job must belong to S. How do you prove for every statement? You see, I have made it clear why there is a suppose statement here. Because I was open about it. I'm trying to make the teaching good. And that's what I'm teaching you how to do. And you might say to me that you have no interest in teaching mathematics. Why am I bothering you with teaching? Actually, you cannot do mathematics without teaching it, and you cannot teach it without doing it. There is no distinction. You know where you learn about teaching mathematics? In math courses. And you know where you learn nothing whatsoever about teaching mathematics? In math ed courses. You learn in the math courses how to teach mathematics. This is the secret. Other people won't tell you this. What I've told you will make people very upset. But anyway, so Anyway, it'll come back to the story with the turntable and the lines. Have I told that story here?
Nope. It's a good one.
Some of you have heard it, huh?
It's on your website. But
Yeah.
in class.
Anyway, I didn't know it was on the website. But anyway, nobody reads my website except very few oddballs, right? Right? So, okay, well, okay, I'm not complaining. So, suppose, now how do you prove that every number satisfying this inequality does some job? Suppose that A less than X less than B. That's how you prove that every number satisfying this inequality will do some job. You write a suppose statement. Suppose that X satisfies this inequality, right? Now I'm going to tell you something. I'm going to tell you that since means because of the fact that I know. That's what since means. Because of the fact that I know, since X is greater than the greatest lower bound of S. Since X is greater than the greatest lower bound of S, we know that X, okay, if you're greater than the greatest lower bound, then you don't live in the southeast, right? What? A number greater than the greatest lower bound is not a lower bound, right? If you're greater than the greatest, you're not one of them. We know that X cannot be a lower bound of S. What does that mean? I'm not going to write it, I'm saying it. But this is what you might write. You might put, change color or do something and say, this means that we know. What does it mean to say that a number is not a lower bound of the set? You've got to know the definition. What does it mean when you say a given number is not a lower bound of a set? Not a lower bound. The meaning means what? There exists, right? There exists a number. Talk to me. Say it all. There's a number in the set that is less than X, right? There is. That means there exists. And when something exists, the next word in the proof is chicken. No, what? Is choose.
Can we go over that again real quick?
Going over what? Well, a number is not a lower bound of a set means what? You have to know the definition. A number is not a lower bound means that there exists a member of the set that is less. Okay? It's only a matter of knowing the definition. If a number is not an upper bound, what does that mean?
There exists a member of the set.
This is one of the first things I did when we talked about lower and upper bounds. I said, what does it mean for a number to be, a number W is an upper bound of a set when something. And then I said, what does it mean when a number fails to be an upper bound of the set? It means there exists at least one member of the set that is bigger. That was the time to fix that, not today. You see, you have to know those definitions. So this number X is not a lower bound of S. So we know that there exists a member of S that is less. And if something exists, not chicken, choose. Choose a member, what should we call it? P of S such that P is less than X, period. Now I'm going to tell you, since X is less than the number B, which is the least upper bound of S. Isn't that given? Isn't that from the information, right? We know that X cannot be an, with less than the least, it's not one of them, right? BMW argument, not an upper bound of S, right? Less than the least upper bound, it's not an upper bound, okay? If a person is younger than everybody in this room, then that person can't be in this room. If a person is younger than the youngest person in this room, that person is not in this room. Very simple idea, okay? And we're using the same thing over and over again. And the way to get this is to be rewriting. So X is not an upper bound of S. What does that mean? X is not an upper bound. You need to have resolved for yourself now, weeks ago, that a number fails to be an upper bound when. What does that mean? Number fails to be an upper bound when there exists at least one member of the set that is bigger. And what do you write when something exists? Chicken, choose. Choose a member. We have to just give it a name. What should we? C of S such. Once we used P, let's use Q now. I don't care. You can call it C. You can use any name you like except A or B or big S or X, right? Because those are in use. Or P. Okay. Choose a number Q of S such that X is less than Q. From the fact that P is less than X is less than Q, and the fact that both P and Q are in S, we conclude that X belongs to S. You see? Now, folks, I have said to you, a number below A never belongs, right? A number above B never belongs. A number strictly between A and B always belongs. Therefore, what is the set S? I will now make the conclusion. Therefore, S is one of the intervals. This this one, this one, and which one have I not put? Right?
Technically, it's not all of them.
No, that's all there is.
But, I mean,
Numbers strictly between A and B definitely belong. Numbers to the left of A, to the right of B never belong. A and B, I have no idea. So therefore, the set S is the open interval running from A to B, or that open interval with A chucked in, or the open interval with B chucked in, or the open interval with both of them chucked in. That's a closed interval. See? There we are. So we've proved that in this case, S is one of the kinds of bounded intervals. Yeah?
So how come we didn't suppose that A is less than or equal to X is less than or equal to B?
Because I don't know whether or not A or B belongs to S. I don't know. My purpose was to explain that any number that is strictly between A and B must belong. That was my purpose. And you could have guessed that by looking at the proofs of the other cases that we did before. By looking at what we did in those cases, because I mean, A is inf S and B is sup S. Do they belong? I have no idea. But I'm going to tell you that a number above sup S, a number above B, definitely not. A number below the number a, inf s, definitely not. Now, the meat of the proof is to explain that any number that is strictly between a and b must belong. And for this purpose, we needed, because I said x is less than a, less than the infimum. So it's less than. You understand? Where am I? I'm in the wrong place. Since a since x is less than the least upper bound, it's less than b, less than the least upper bound, so it's not an upper bound. Wouldn't have been good enough if you had less than or equals, would have destroyed that. Okay? To be able to make a definite statement, this number cannot be an upper bound because it's less than the least upper bound. Okay? If I told you a certain individual has an age that is less than or equal to the age of the youngest person in this room, what can you conclude? The answer is, I don't know. But if the age of a person is less than the age of the youngest person in this room, now I can tell you that person is somewhere else. Probably in Sydney, Australia or somewhere. Okay? That's the story. Very well. Now, I want you to take a brief look in the text about integers. I'm going to make a quick statement to you about integers. And I'm going to say that the least positive integer is 1. Is that a reasonable supposition about what integers do? And the sum and difference of any two integers is always an integer. If you add or subtract a couple of integers, you always get an integer. By the way, you can also multiply. I don't want to start fussing. You can't always divide, okay? Sometimes divide. You can divide 14 by 7 in the world of integers.
But not 7 by 14.
Okay? But a critically important fact about the system of integers is that the smallest positive integer is 1. And I'm going to pose a question to you. Is the set of integers bounded above? What do you think?
You can always add 1.
Definitely, it seems to be out of the question, right? And yet there is something very murky here. There is no question that no integer could be an upper bound of the set of integers, because if p is an integer, p plus 17 is another integer bigger than p, you see. That doesn't answer the question. Because if x is a real number, the question is, how do you know there are integers greater than this x? If you were to question whether or not the set of integers is bounded above, you would have to ask yourself whether any real number could possibly be an upper bound of the set of integers. And I'm sure that the answer no is quivering on all your lips. Am I correct?
Upper bound need not
That
be part of the set.
I mean, you would feel, look, if x is a real number, don't you think there jolly well ought to exist some integers above x? Well, your intuitive feel about the number line says that, but I do want to tell you that in the context of mathematics development, we think of the system of real numbers as an arithmetical system with a couple of binary operations called plus and times, doing various jobs, together with an additive identity 0 and a multiplicative identity 1, and a certain stuff about subtraction and division, okay? By now you're basically thinking of the system of rationals, right? And certain basic rules of inequalities must apply. You know that given any two real numbers, x and y, either x is less than y or y is less than x, or x and y are the same number, and one and only one of those conditions holds. So we have what is called a total order. Well, also, if x is less than y and y is less than z, then x must be less than z. That gives us what we call a total order. And so an arithmetical system with that's called a totally ordered field. And then there is the statement of completeness, that every set that is non-empty and bounded above has a least upper bound. And by the way, as you learnt from me last week or sometime, we also know that every non-empty set that is bounded below has to have a greatest lower bound. Required some careful writing there. Now, it turns out, if you ignore the completeness, that if what you want, can you maybe close? If what you want is a total order, a less than that does the kinds of things you expect of a less than, and the rules of inequalities that must apply for numbers. The kind of rules I'm thinking of is that if A is less than B and you add a number to both sides, a number Charlie to both sides, and you take A plus Charlie and B plus Charlie, A plus Charlie will be less than B plus Charlie, you see? And by the way, if A is less than B, you can multiply both sides by Charlie, as long as Charlie is what?
Non-negative.
If you want a less than, positive, right? And you can multiply by a negative number as long as you do what? You reverse the inequality. Actually, the one follows from the other. If I were teaching you algebra, I'd fuss about that. I refuse to do that here. And that kind of system is in the text. I call that a totally ordered field. I don't know whether any of you have come across the word field in any math course. Nothing to do with electric fields, by the way. It's a different word. Or anything in Calc 3 where we talk about. Yeah, that's nothing to do with that. Okay? But anyway, what I'm saying is that, believe it or not, I can cook up, and I'm not going to show you in this course, I can cook up an example of a totally ordered field, an arithmetical system with an additive inverse 0 and a multiplicative inverse 1, and a less than, and all the rules of arithmetic that your heart could desire, distributive laws and all that stuff, and the rules of inequalities. And I can give you an example of such a system, and the set of integers there can be bounded above. How shocking is that? Such fields are called hyperreal residue class, hyperreal totally ordered fields. That's what they're called. There's a very good book on the market. You're not ready to read it. It's a book called Rings of Continuous Functions. It's an algebra book, actually. I never thought it was an algebra book. I thought it would sort of skirted the world of topology and analysis. But one of my teachers at the University of Wisconsin said, nonsense, it's an algebra book. And he was by trade an algebraist. said, okay, I'm going to call it an algebra book, by Gilman and Jerison, Rings of Continuous Functions. It is bristling with examples of totally ordered fields in which the sets of integers there are bounded above. However, if you have a totally ordered field and you have a completeness statement that every non-empty set that is bounded above has a least upper bound, actually there's a theorem that I'm not quite going to drag you into in this course, that if you have any two fields like that, they are exact carbon copies of one another. You can find a 1-1 function from the one onto the other that preserves absolutely everything. They might as well be the same system. But in a field that is complete, the set of integers will never be bounded above. So that your intuition about the number system is correct for the number system, but I want you to know that it uses the completeness. And we're going to have a little theorem about sets of integers that are bounded above. It's 5, 9, 1. So here it is, and I will call it 5, 9, 1, sets of integers that are bounded above. Well, of course, the set might be empty, right? It's boring. Okay, I'm going to tell you what I have in mind. We assume that S is a set of integers. Integers, okay? I didn't say the set of integers. If I say the set of integers, I might as well use a Z, because that would be the set of all integers. When I say S is a set of integers, I mean S is any set whose members have to be integers, okay? And that S is not empty, and that S is bounded above. I shall prove that S must have a largest member. Intuitively, wouldn't you feel that is reasonable? I'm going to prove to you that if you ever have any set of integers that is bounded above a non-empty, it's got to have a largest member. If I could prove this theorem, wouldn't it be obvious that the set of all integers cannot be bounded above? You see, the set of all integers can't have a largest member, because if you take any integer, you can add 17 and get a bigger one, right? So I'm going to tell you that when a set of integers is non-empty and bounded above, it's got to have a largest member, and here's the proof. Here's the proof. I'm going to use contradiction. Question?
Yes. Wouldn't this be similar to the axiom of completeness, I guess, in a sense? Because
I don't know what you mean by similar. You have to give me a definition of that word. I'm going to tell you that using the axiom of completeness, we are able to prove in the system of real numbers, where there is an axiom of completeness, that when a set of integers is non-empty and bounded above, it's got to have a largest member. That's what I'm saying. I'm hesitant to say similar. I don't know what you mean. I don't know what the word similar means in this context. So I'm going to prove this, and I'm going to use a contradiction proof. I don't have to, but I think it's about time. I never use a contradiction proof without saying so. I'm going to say, to obtain a contradiction, we assume that S does not have a largest member. If I can get a contradiction from this, what will we conclude? That S does have a largest member, right? Okay. I'm now going to talk to you. The set S is non-empty. Did I say that? And the set S is bounded above. So I'm going to say we define W to be sup S. I'm allowed to do that because when a set is non-empty and bounded above, has the largest member, right? Here's a question. Is W an integer? The answer is, for the moment, I have no idea. Maybe it is. Unofficially, bloody well better be, right? But for now, I'm not, makes my head hurt to worry. See? Tell you later it is. Okay, now, we define W to be sup S. Fair enough? Okay. I'm going to tell you something. Since W minus 1, I have no idea whether that's an integer or not, right? When you say, well, in my bones, I feel it's an integer. Okay, well, but I don't know. But W minus 1 is less than W. That I can tell you. It's a number less than W. Fair enough? And W is what? What is the definition of W? W is begins with L. Lewin. No. Least upper bound of S. When a number is less than the least upper bound of a set. The old BMW argument applies. A number is less than the least. It cannot be. Since W minus 1 is less than W, we know that W minus 1 cannot be an upper bound of S. Is that fair enough? Cannot be an upper bound. Now I'm going to ask you for about the 5th time today, what can you do with information that a number fails to be an upper bound of a set? This has happened 20 times for us and a few times today. When a number is not an upper bound of a set, what can you do with that? It's not an upper bound. That means there must exist members of the set that are bigger. So when something exists, what's the next word? Choose. Choose. Let's make a new line. Choose a member, should we call it X of S, such that W minus 1 is less than X. The number W minus 1 is not an upper bound of S. Using that information, I chose a member of S that is bigger. Okay? Of course, you never use of course. Of course, don't believe me, right? Of course, X is less than or equal to W. Isn't that right? But I can do better. I know that X cannot be equal to W because what? Because we assumed, right? We assumed that S doesn't have a largest member. You see? So I'm telling you that X, I know, therefore, let me say this. X is less than W, right? Less than, right? Less than W. Yes, then. W, that's a W. We know that X can't be more than W, but it can't be equal to W either, because the supremum W of S must not belong to S, otherwise it would be the greatest member. If the supremum of a set is one of the members, it's the biggest, is it not? This is a principle that we've resolved together. You see, I'm standing on the shoulders of earlier material all the time. Nothing goes all on its own here. Nothing anywhere in mathematics, not in any course, actually. So X is less than W, and please remember that W is the least upper bound of S, and don't forget that W is sup S. Okay, haha. Now we know that X cannot be an upper bound of S, because what? Because X is less than the least upper bound. Okay. An upper bound of S cannot be an upper bound. Okay? So now what? When you know that a number is not an upper bound of a set, what is it that you know? You know that there exist members of the set that are bigger. When something exists, you say, choose. Choose what? Choose a member, which I think I'll call it Y, of S, such that X is less than Y. Okay? Now, we have the inequality. Firstly, W minus 1 was less than X. Reasonable? And X is less than Y. You understand? And Y is less than or equal to W, as a matter of fact, is less than. I don't care. You want to write less than or equals? Be my guest. It's fine. Be good enough. But how do you know that Y is not more than W? W is the supremum of S, is an upper bound. Y is certainly not more than W. How do you know that Y is not equal to W? Y is a member of S. W cannot be a member of S, because we said that S doesn't have a largest member. Do you understand? Okay, well, I've got news for you. Zero is definitely less than Y minus X. I hope you believe that. Is that fair enough? Now, Y minus X is definitely less than W minus X, because Y is less than W. Do you understand? And if you're subtracting X, you're subtracting more than if you're subtracting that. Do you understand? If I were to write W minus this, I'm subtracting less now, so actually gets even bigger. Do you understand? The less you subtract, the more you get. And this number happens to be 1. Now we have an integer, mainly Y minus X, between 0 and 1, which is the desired contradiction. Bit of a tricky proof. After you've written it out 5 or 6 times, you'll understand it. Will you understand it now because you watched me do it? Hell no. You won't. You never understand anything when you were listening to somebody else's voice. You have to write it yourself. But let's go through this again. We are assuming that we've got a set of integers, and the set of integers is non-empty and bounded above, and it is my task to prove that this set has a greatest member. You understand? I'm going to do it by contradiction, even though I could have written a direct proof. I thought it was a good opportunity. This is a good time to do a proof by contradiction. I haven't done enough. So I said, to obtain a contradiction, I'm making it clear as I begin what I'm about to do. To obtain a contradiction, I'm going to make the assumption that S does not have a largest member, and we're going to get a contradiction. And the contradiction that's going to come out is that we're going to get an integer between 0 and 1, and the contradiction is because I said the initial basic fact about integers is that 1 is the least positive integer. You can't have an integer that is positive and less than 1. 1 is the least positive integer, you see? So you find an integer between 0 and 1, that is impossible. You understand? Okay, so let's go through the proof. First, I use the completeness axiom, and I make a definition. We define W equals sup S. Okay? Having done that, I look at the number W minus 1. I come down a bit. And I say, this number is less than the sup of S, less than the least upper bound. If you're less than the least upper bound, you don't live in the southeast, right? You are not one of the upper bounds. W minus 1 cannot be an upper bound of S, okay? Now think, what does it mean when a number is not an upper bound of a set? What does it mean when a number is an upper bound of a set? And what does it mean when a number is not an upper bound of a set? By now, you should be rattling this off, because this is what you studied when you wrote the other proofs that dated back a couple of weeks. When a number is an upper bound of a set, you know that the number is less than or equal to every member of the set. What does it mean when a number fails to be an upper bound of a set? It means there exists at least one member of the set that is bigger. You understand? Choose a member of S that is bigger than W minus 1. And I want to tell you something. This thing I chose can't be more than W, because W is an upper bound of S. And X can't be equal to W, because that would make X the biggest member of S. And what did I say? There is no biggest member. Therefore, what do I know? I know that X is less than W. Aha! So I'm going to repeat my reasoning. I'm going to say, here is a number that is less than the least upper bound of the set. As less than the least upper bound, it can't be what? If you're less than the least, you are not one of them, right? X is not an upper bound of S. What does it mean to say that X is not an upper bound? It means that there exists a member of S that is bigger. Choose. See? And now I've got two different members, two members of S that are unequal to one another. Both of them between W minus 1 and W. Look at a picture. How far do you walk from here, from W minus 1 to W? How far do you walk? 1 unit. Well, and this is strictly in between. So how far do you walk from X to Y? Y minus X is less than 1. You understand? Look at a picture. You don't have to go through these inequalities, because that's obvious. Look at a number line. Here's W minus 1, and there's W. The length of that little red stick is 1, and X and Y in between. So the distance from X to Y is less than 1. You understand? Y minus X is less than 1. So it's an integer, strictly positive and strictly less than 1. That's a contradiction. Okay? I have two comments to make to you. After you've rewritten this proof, you're all going to sit down and write a proof. What proof? What do you think you should now write? Whenever a set of integers is non-empty and bounded below, it's going to have a least member. Do you understand? It should be so clear to you that you should do this, I shouldn't even have to tell you. You should be driven in from inside to want to do that. Give me a moment. Now I'm also going to tell you another thing. In the exercises on upper and lower bounds, one of the exercises there, I can't quite remember what it said, but I think there was a non-empty set that was bounded above and didn't have a greatest member, and we had some number less than the sup. And I said, prove that there must exist at least 2 different members of the set above this member. Okay? We have snuck in that exercise. You can go back and do that exercise now. Suppose a set E, it has no largest member and it's bounded above a non-empty. And you take a number less than the supremum. Well, it's not an upper bound. Choose a member of the set that is bigger. That member that you chose can't be more than the supremum, but it can't be equal to the supremum because I said no largest member. So therefore this thing is also less than the supremum, so it's also not an upper bound of the set. You can get another member of the set that is bigger, and that gives you 2 members. If you want to repeat that argument, you can even get 3 members. If you're willing to sit for long enough, you can get 3 trillion members. If you're willing to sit forever, you can get infinitely many members. I did not all. That's another story. That depends on some aspects of set theory. But infinitely many. So I just wanted to mention that that exercise now should be easier than it was. Talk to me.
How do you know that the supremum of S exists?
Because S is non-empty and bounded above.
But isn't that just for real? Like, because the axiom of completeness
Says any set of real numbers. A set of integers, of course it's a set of real numbers, you see, within the real number system. Every set that is non-empty and bounded above has a supremum. But your question actually has some valid points in it. You're saying, is it okay in a special case? And the answer is yes. If it's okay in the general case, it's okay in the special case. So if I say to you, every person in this room loves ice cream, you can make a conclusion from that every red-headed person in this room loves ice cream. You see?
Even if there are no redheads.
Yes. Every red-headed person in the room loves to copy Encyclopedia Britannica. I don't know if you know what I'm talking about. Anybody know that Sherlock Holmes story? Oh well. Question. Let me see if we do it before. Yeah.
So could we have stopped at, did we have to choose Y as well? Or could we have stopped at XN and we found that X
I used these 2 numbers to find myself a definite known integer, because the difference of 2 integers and integer, that is definitely positive and definitely less than 1. If you think you can handle it without the Y, write me the proof and I'll have a look. But I can't see how.
W is not necessarily
if you're saying, could we have not done it? Write it up, and you may be right, but I will know only when I read it. Yeah.
So for the set of all positive integers, does that make 1 the nth of that set?
1 will be the least member and therefore will be the nth. I agree. And of course there is no sup, it's not bounded above. And by the way, it now follows that the set of all integers is not bounded above. Okay? The set of all integers fails to be bounded above. Maybe I'll just write this in here before I stop. The set Z cannot be bounded above. Because why? You'll write because. Because it doesn't have a largest member. Any set of integers, if it's non-empty and bounded above, has got to have a largest member. This set doesn't have a largest member, so it can't be bounded above. Yeah?
So is the whole goal of this proof to choose an x that couldn't be an integer, essentially? Because of the way...
I don't know about any x that isn't an integer. The particular x in this proof was an integer.
But the contradiction I thought was that it couldn't be because it's greater than w minus 1, and the next integer that would be greater than w minus 1 is w itself. That's be less than
Basically, in this proof, we chose two definitely known integers, x and y, satisfying a certain inequality that turned out to be impossible. On the one hand, they are integers, so the difference is an integer. But the difference is positive, and the difference is less than 1. Trouble. Got a contradiction. Folks, we need to stop. It's getting late. But go do some thinking. The questions coming from you, whether they're right or wrong, are all good. Everybody. So here we go.